Hello everyone, welcome to Probability and Statistics for Data Science. In previous videos we have explained how to model uncertain discrete quantities using discrete random variables. Essentially what we do is we estimate their probability mass function, their PMF, from data. There are two ways to do it. You can do it the non-parametric way using the empirical PMF, or you can do it the parametric way where you design a parametric distribution and then choose the parameters using maximum likelihood. This begs the question, which method is better? And the answer is that it depends on the situation, and it's very important to know how to evaluate a model in practice. And that's exactly what we're going to do today. We're going to compare parametric and non-parametric models and explain, what kind of, explain their pros and cons, and also explain how you should actually evaluate them in practice. Again, that's the motivation. We have two approaches to estimate PMFs from data. One is the empirical PMF, which is a non-parametric model. The other is using a parametric model based on some predefined distribution that we have designed according to the phenomenon that we're interested in, making some assumptions that hopefully are reasonable. So which one is better? And the answer, often in life, is that it depends on the situation. So our goal is to learn how to evaluate models in realistic situations. So let's take a look at some real data. We're using again this example where we want to model the length of the consecutive streaks of free throws made by Kevin Durant. Okay, a streak of free throws is when he makes 10 in a row and then he misses, or he makes 5 and then he misses. Okay, that would be streaks of length 10 and 5 respectively. And we have some real data. We've gathered 377 streaks from 3,000 free throws that he shot in the NBA. Okay, the non-parametric model was just the empirical PMF where we say, okay, what's the probability of a streak of length 2? Whatever fraction of the streaks have length 2 in our data set. We also had a parametric model, which is essentially equivalent to a geometric distribution where we assumed that each free throw was independent and had the same probability of going in. And that's what the corresponding PMF looks like. We already explained how to fit it using the data, using maximum likelihood in a previous video. So this is how the parametric model looks, and this is how the empirical PMF looks. We had already discussed that the empirical PMF looks kind of noisy and the parametric model looks, kind of smoother, which is nice, but that's no reason to prefer one over the other. So how do we evaluate these two? How do we compare these two models? The first question that could come to you is, let me see which one fits the data that I have best. I want to give you a moment to think about this, so please pause the video and think, which one fits the best and is that a good evaluation? So the answer is that the empirical PMF is amazing because it completely fits the data exactly because we have defined it to be the empirical probabilities of each of the streaks. So its error is 0 if you want. Is this a good evaluation metric? It kind of sounds too good to be true to have an estimator that is equal to 0, and we see that it looks kind of noisy. So what is the problem with this evaluation? Again, please feel free to pause the video if you want to think a little bit about it. I think it's probably worth thinking about it before hearing me tell you why. And the thing is that you cannot use the same data to fit a model and also evaluate it. This is as if I gave my students the solutions to an exam and then I put the same exam. They can just parrot the solutions without learning anything. A model can do very well on the training data without actually learning anything about whatever we are modeling. I'm not saying that's the case for the empirical PMF, but it could be. So that evaluation strategy is no good. What about this evaluation strategy, which you will actually see in many research papers, okay? So we can, since we don't have ground truth for our real data, we can say, okay, how about I simulate data, assuming this parametric model, which I think is reasonable, and then I see if I can recover the true parameter of the parametric model. Okay, so we're gonna say, I'm gonna fix theta to be 0.875, and I'm going to generate new data according to this model, which I think is super reasonable. And I'm going to generate 3,000 free throws like that, and I'm going to see which model allows me to approximate the true PMF better. I know the true PMF because I have decided what the true PMF is. I'm generating some synthetic data based on it. If I do that, we already discussed this a little bit at the end of the video on maximum likelihood. I get this maximum likelihood estimate. So the parametric model is amazing when you compare it to the true PMF, which is this black line. It's essentially on top of the line, right? Because the parameter is actually very close to a true parameter. In contrast, the empirical PMF is much worse, right? It's like it's very different to the true PMF. And this happens when we do it over and over. We repeat the same experiment with 3,000 more synthetic points. Again, the parameter is quite close to a true parameter. We get an amazing estimate with the parametric model. And again, much better than with the non-parametric model. All right, should we conclude that the parametric model is better? Case closed. Again, if this is not clear, if it's not clear to you, why not? Pause the video and think a little bit about it. The issue here is that we're creating synthetic data based on assumptions that are reasonable, maybe, but they are probably violated in the real data, or they could be violated in the real data. So the distribution of the synthetic data is different from that of the real data, probably. And on top of that, it's kind of unfair, right? Because we have assumed the same parametric model that we're using to fit. It's not as bad as the first option. In the first option, you can overfit. Here, we're actually seeing whether maximum likelihood gives us a good estimate of the true underlying parameter. So it's not as bad as the first way of evaluating things. And this can actually be very useful to at least evaluate this model that you're using to estimate the parameters and realize how much error you can expect on those parameters just from the number of data that you have. But still, it's not a fair comparison. Okay, the real data are not generated by the parametric model, so we cannot evaluate the two models based on that assumption. All right, so what do we do? How do we evaluate? And the answer is what you should do in practice if you're doing probabilistic modeling. You need to gather real held out data, which is the data that you want your model to do well on. And that's exactly what you need to do. And here what I did is, and just to make sure that we have like our machine learning lingo in order, the training set are the data that we use to train or fit the model. And then we fix that model, we don't touch it anymore. In the case of the parametric model, we don't touch the theta anymore. In the case of the non-parametric model, we just keep that PMF, we don't touch it. Then we evaluate it on new held out data, which we call the test set. The way we're going to, here, just as an example, I gathered 3,000 free throws, the first 3,000 free throws in Durant's career as a training set, and then the following 3,000 free throws as a test set. So there we're going to see how good our models are. We're going to be quantitative about this. We're going to take a look at the probability that we observe in the test. So this is going to be the empirical PMF, but of the test data, because that's kind of a reasonable thing to try to estimate, right? What is the probability of seeing a streak of, let's say, length 3 or 4 in the test data? Realize that the test data, unfortunately, is limited. So there's going to be noise there, but that noise is not going to be the same noise as in the training set. So we're not going to be able to overfit it, if that makes sense. That's a little bit of a subtle point. The point is that we're going to compare the estimated probabilities to what we observe, the estimated PMF to the observed PMF on the test. Again, and we're just going to sum over everything and take a square root. That's called the root mean square error. Just a way to just aggregate the errors at each streak length. All right, so first let's take a look at the non-parametric model. Before seeing the results, I think it would be good to review the pros and cons of this model. First, we have to say that even though we call this a non-parametric model, it's not really true that it's non-parametric in the sense that you don't estimate parameters. Of course, we're estimating stuff. We're estimating every single entry of the PMF. In our free throw example, we're considering streaks until length like 55 or around there. So we're estimating 55 numbers as opposed to one number for the parametric model. We observed 370 streaks, So that's why the results are so noisy, right? We're trying to estimate 50 numbers from 370 data points, and for that, some of those numbers, they correspond to streaks of quite some length, like streak 50, streak of length 50, of length 49, that has low probability. So if we only see 300 and something streaks, we're probably not going to see them. Okay, that's why we had so many zeros for the longer streaks. Okay, so the good news is that the non-parametric model is going to have a lot of flexibility. We're not making these assumptions that we made for the parametric model, which we're pretty sure don't really hold. That's good. It can adapt to like whatever structure it sees in the data. The bad news is that it has a lot of parameters to estimate, so it can it will be noisy, and it can actually overfit whatever it sees in the training set because of this flexibility. Okay, it requires a lot of data to not overfit. Hopefully that makes sense. I should say what overfit means. It means that overfitting means fitting the training set really, really well, the data that you're using to fit the model, and but not in a way that generalizes to the held out data in the test set. We're going to see exactly what I mean in a moment. So the test RMSE of the test error of the non-parametric model is this. It's about 7.6 times 10 to the minus 3. We will compare it to the parametric model. This number by itself doesn't tell you much, but it's instructive to think what the training RMSE is. And the training RMSE for the non-parametric model is actually 0. Okay, so, these two numbers are definitely quite different. It seems that you're fitting the training data much better than the test data. We shouldn't really hold this against the non-parametric model because by definition it's going to fit the training data perfectly. Okay, here, when we compare the empirical PMF obtained from the training set and the test empirical PMF, we see that indeed the empirical PMF is quite noisy. So we were seeing these weird patterns in the training set. It looks like these were just noise from the fact that we have limited data, because the training data does not exhibit the same patterns. Similarly here, we're saying, oh, if you remember in the video on, I think the video on the geometric distribution, probably we're saying this. No, sorry, not on the geometric distribution, the video on estimating the PMF on probability mass function, where we're showing how to use the empirical PMF to estimate from data. We're saying that it's kind of weird that here a lot of them are 0 and then some are non-zero. That looks like noise, and indeed it is noise. We see that because, for example, here and here, the test and the training PMFs differ, and that's caused by the fact that the model is super flexible in the sense that it can give different probabilities that are completely decoupled to these guys, which is a bad thing because we don't have enough data to constrain all of those parameters that the non-parametric model has, so you end up overfitting the training set. All right, so what about the parametric model? The parametric model gives you a predefined shape for the PMF that constrains the model. It depends on a very small number of parameters, typically. In our case, just one parameter, as opposed to the 55 parameters that we need to estimate with a non-parametric model. So the good news is that it cannot overfit easily. If you see, like, it cannot overfit the noise in the training set due to the limited data. The bad news is that it can underfit, meaning that if it finds some structure that is really there, but is not consistent with the assumptions that we made when we derived the parametric model, it will not be able to take that into account. Okay, and that is called underfitting because you're not fitting the data well enough. Okay, so let's first take a look at what the parametric model does on the training set. It gets this error on the training set. Okay, like it fits it pretty nicely. This is just to compare to when we look at how it fits the test set. When we look at how it fits the test set, it fits it pretty well too. In fact, the test error is, number one, smaller than the non-parametric one, which was like 7.6, so, and quite a bit smaller. So this indicates that it generalizes better. In this case, the non-parametric one is overfitting too much. and the parametric one is not overfitting, and the assumptions indeed seem to be quite reasonable. It also has an error that is quite similar to the training error. Okay, very, very similar, which means that we're not overfitting the training set at all. We could perhaps even improve by trying to fit the training set a little bit better, maybe modifying our parametric model in some way. Right, so our conclusion here is that the parametric model is better than the non-parametric model. In general, for other situations, it will depend. So when will a parametric model be better than a non-parametric model, or vice versa? If you don't have a lot of data, but you have a very good knowledge of the data generating process of the phenomena that you want to model, what should you use? Hopefully you said parametric model. If you have very little knowledge about the data generating process, but you have a lot of data, what should you probably use? Well, the other option, no? Non-parametric model, but hopefully this makes sense given our discussion. Okay, so to finish, we're going to look at another example with real data, where we're going to look at telephone calls that are arriving in a call center in a bank. Imagine that you own the call center or something, or you're hired by the call center, and you want to know what's probability of obtaining different number of calls so that you hire people to answer those calls. So we want to model the number of calls occurring between 6 a.m. and 7 a.m. on weekdays, between Monday and Friday. We have a training set that are calls from January to June in 1999. And we're going to use a test set, because now we know that this is the way to evaluate models using held out data, that includes calls from July to December, again of 1999. Okay, we want to somehow estimate a PMF from this data and use it to estimate the PMF that we would observe here, which we know because it's actual test data. It will give us a way of evaluating the possible models in a fair way. Okay, so first, the non-parametric model is obvious. We're just going to use the empirical PMF again. Let's design a parametric model. We're going to make the following assumptions. We're going to assume that the calls arrive independently. This is not necessarily the case. Imagine there's some financial crisis and people start calling the bank all at the same time. In that case, they wouldn't be independent, but in general, we assume that everyone is in their own place and there's no event that kind of makes them dependent. So we assume that the calls are all independent. We assume that the probability of a call in a period of small length t is proportional to a rate of calls that arrive at that time and is constant. So basically this kind of says that the probability of seeing a call in any small interval within that hour is kind of constant. This wouldn't happen if we consider the whole day, right? Because there are more calls at certain times of the day, less calls at other times of the day. And that the probability of more calls when we pick a very, very small interval is negligible, which is quite reasonable. So maybe these assumptions sound familiar. They hopefully sound familiar if you've seen the video on the Poisson distribution, because according to these assumptions, our parametric model is just Poisson. Okay, so we're going to use a Poisson model. So now in order to fit our Poisson model to the data, we need to apply maximum likelihood. So we're going to write down the likelihood of the Poisson, and this will allow us to review a little bit maximum likelihood. So remember that in maximum likelihood, what we do is we assume that the data are IID, they're independent, and they all have the same PMF, they're identically distributed. And we write the probability of the observed data as a function of the parameter of the distribution that we're interested in. So in this case, the parameter is lambda. So here we're going to plug in the PMF of the Poisson that depends on lambda, evaluated at each data point xi. Okay, that's what the Poisson distribution looks like. And now, because this would give us a very, very small value and would give us some numerical instability, we're going to take a log. We can take a log because that doesn't change the maximum, where the maximum with respect to lambda is going to be. Okay, so this is what happens after you take the log. The product becomes a sum. And now we take that expression and we maximize it with respect to lambda. First, we take the first and second derivative. The derivative of log of lambda is 1 over lambda. The derivative of lambda is just 1. That's the first derivative. The second derivative is equal to this because 1 over lambda, the derivative of that is just minus 1 over lambda squared. This is negative. That's really good news because it means that the function looks like that. It's concave. So we can look at where the derivative is 0, and that will give us the maximum, the lambda that maximizes this expression. Setting this to 0 tells us that the maximum likelihood estimate of lambda should be the sum of all the data points divided by n. So basically it's the average number of calls. So hopefully, well, not hopefully, let's do this thing where we take a step back and we think about whether this makes sense given the assumptions of our parametric model. Lambda is kind of the rate at which calls arrive. So since we're looking at calls over 1 hour, it's very reasonable to say, okay, let's use as the average calls that are arriving in an hour as the rate of calls per hour. So it makes a lot of sense that you would just use the average in this case. Okay, so now we have our parametric model. We can compare it to our non-parametric model, which is just the empirical PMF. First, let's start with the parametric model. We're comparing the parametric model to the test empirical PMF, just as we did with the free throws. What we see, it's not that bad, right? It's not perfect, but it's not that bad. This is just using 1 month of training data. What happens if we increase the number of months of training data? What happens is that the model barely changes a little bit, but really not that much. The model is super stable because we're just estimating a single parameter. So even when we gather more and more data, it cannot really adapt to, you know, this weird stuff that it's seeing in the distribution, even though probably it should to some extent, but it doesn't have the flexibility to adapt. Let's see what happens with a non-parametric model. When we just use 1 month, it's actually quite catastrophic. Why is it catastrophic? Well, it looks like in January, there are many cases where we don't see any calls within this hour. So that is probably, my conjecture is because it's probably holidays. And the model, and then in the test data, that doesn't happen anymore. So that actually hurts the model a lot, even though it's probably meaningful structure within the training set. And that's something very important to think about, right? You have a test set. It's in realistic situations that the training set and the test set often will not have exactly the same distribution, and you have to ask yourself how that affects the results. Notice that if we go back to the parametric model, which is only trained on January, because of the shape of the Poisson distribution, it cannot fit anything here, like it cannot bring this single point up there if it also wants to fit the rest of the points. It doesn't have the flexibility to overfit to that. Again, this is overfitting because we don't see it in the test set, but it could be that could be important for the test set, and in that case, the parametric model wouldn't do its job well. Okay, so let's go back to the non-parametric model. Super flexible, it allows us to model that. However, it hurts us because we don't see that in the test. If we had in the test set, if we had January from the following year, this would actually be good. And in general, what we see is that it's very noisy. Okay, you see like very, very noisy with respect to the real data. As we increase the number of data, and the problem is that, right, that you're trying to estimate a lot of parameters, 24 parameters, from not that many data, 31 days. And not even 31 days, right, because we're only considering weekdays, so about 28 days. So the number of parameters and data for the non-parametric model, if you just use 1 month, are essentially the same. That's very problematic. When we increase the number of training data, we start seeing that the model starts looking a bit less noisy, and eventually it looks still kind of noisy. That looks like noise, but still, but it kind of adapts to the general shape of the distribution pretty well. In more of it's still noisy, but it kind of has the flexibility to start realizing that the distribution looks something like that. Whereas the Poisson, again, is constrained to have this Poisson shape. It doesn't completely manage to do that. This, by the way, tells us that the Poisson assumptions don't completely hold in this case. Okay, but let's look at the test RMSE, the error that we see. This, we should remember what we were seeing. We were seeing indeed that for one training month, the non-parametric model looked super noisy, and indeed its error is super high, much higher than the parametric one. We also saw that the parametric model didn't really change where we changed the training data. And indeed, we see that, its error is pretty much constant, roughly. We also saw that the non-parametric model seemed to be improving quite a bit as we gained as we gathered more and more data. And that's exactly what we see here. Okay, it improves to the point where it eventually overtakes the parametric model for when we have 6 months of training data. This tells us that in this case, the assumptions of the parametric model are not completely reasonable. And if we have enough data, it's better to use a non-parametric model that has the flexibility to adapt to this structure in the data that cannot be accounted with the parametric model. And that's all I got. We have learned how to evaluate models in practice and also the advantages and disadvantages of parametric and non-parametric models for discrete data. Thank you very much.